Thanks, Veronica. Today's lecture, I have consolidated the lecture notes and the template into a single lecture 4. So just download the lecture 4 template from the wiki if you want to follow along. And if you remember last day, we had started talking about entanglement, and we proved this the Schmidt decomposition property of bipartite entangled states, which was really just secretly the singular, or not even so secretly, it's the singular value decomposition applied to the matrix coefficients. And today we're going to say a little bit more about entanglement, pure state entanglement, bipartite. It's an ocean of things we could discuss, but I want to move on to error correction because I know that error correction is going to play a significant role in future courses. So that's what we'll do for the second half of the lecture. So I'll share my screen. And I'd like to spend a few minutes just talking about what is so special about entanglement. Why do we care about entanglement? What's different about entanglement versus classical correlation? And I'll give you 3 examples of interesting things entanglement can do, just so that you have these in your pocket and you can think about them. Some of them do play a role in holography or high energy physics. And the first very simple one is something called superdense coding. And the situation is that we have our Alice and Bob. Remember, time runs from left to right, and the purple lines indicate some quantum information. And each one of these subsystems is going to be, let's call it A and B. They'll be qubits. And they're going to be sharing a maximally entangled state. I'll drop the normalization. So that's this state right here. Now, Alice, what she wants to do is she wants to send a message to Bob. And she's, we see here that she has the ability to send 1 qubit from Alice to Bob, but Alice wants to do something more than that. She wants to send a message which is classical, and it's one of 4 possibilities. So 0, 1, 2, or 3. So I'm drawing this thought bubble here. So she has a message in her head, J, and she wants to communicate J to Bob. We proved this Holova bound last day that proved that a single qubit can't send more than 1 classical bit's worth of information. And so it looks like she would be sunk. But there's something that can be done here that we could notice that if we define state, say psi sub j, which is the Pauli operator sigma j, acting on 1/2 of this maximally entangled state. And I'm just calling sigma 0 will just be the identity matrix. Then you can verify for yourselves that you get 4 orthonormal states this way. And so what Alice could do is she could just apply the Pauli operator indexed by her message, sigma j, on her half of that maximally entangled state. And when Bob receives just the 1 qubit, he can then measure not just the qubit that was sent, but the qubit and his half of the entanglement. And we'll call this the psi j measurement. And out will come j without any errors whatsoever. And so entanglement can actually enhance your ability to communicate. And this is something that classical correlation simply cannot do. That if an Alice wants to send a message to a Bob, having classical correlation between Alice and Bob in no way lets Alice send information at a higher rate to Bob. But entanglement can double the rate and in some circumstances do more. And so entanglement is helpful for communication in a way that classical correlation is not. So that's one thing that's special about entanglement. There's another way that entanglement is helpful for communication that's kind of dual to what you just saw with superdense coding. And the setup here is, again, we have our Alice and Bob, and their laboratories are separated by this dotted line. And what Alice wants to do is she now wants to send Bob not classical data, but the state of her quantum system. And it's a quantum system that's in her lab, so I'll just call it S. And I've written phi, but I didn't put phi in Alice's head. Let's just say that Alice doesn't even know what phi is, right? There's just a system, and she wants the state of that system to end up in Bob's lab. So at the end of the day, Bob wants to end up with the quantum state phi. And again, let's think that these are all qubits and they share one of these maximally entangled states. And what they're going to be allowed to do, of course, some communication is going to be required. And if Alice were allowed to send Bob a qubit, this would be trivial and easy. But we're not going to allow that. All we're going to allow is for Alice to send a classical message from to Bob. And so, basically Alice is allowed to get on the phone and tell Bob something classical. And of course, you wouldn't think that classical data would be sufficient to send quantum information because that quantum state has these complex coefficients that that vary continuously. And if J is a classical message, you're not going to be able to, even if J was very large, you're not going to be able to send an infinite amount of information and get those coefficients across. Moreover, if Alice tried to measure the quantum state to figure out what to send, measurements in quantum mechanics generally cause disturbance. And so you would think, okay, well, measuring the state to learn what it is and then communicating it is not going to allow Alice to send a precise copy of phi. But what she can do is she can do a measurement, which is actually the same measurement that was used for superdense coding. Right, so these psi j states, which I'll just copy them over so you can see them. So she measures in that orthonormal basis for the SA system. And if she does that, she communicates the J to Bob, and then J, upon receiving the classical, or Bob, upon receiving the classical message J, he just applies sigma J. And the quantum state phi comes out precisely. So again, we see that entanglement is enhancing the ability to communicate in a non-trivial way. And what entanglement is actually doing here is entanglement is allowing you to upgrade a classical communication channel, the ability to just send messages that we're used to, bits, into a quantum communication channel, one that can send the state of a quantum system reliably. And this looks a little bit like magic. Why is it called teleportation? Well, the quantum state phi was in one place, it kind of disappears and reappears somewhere else. And in between, it exists, it seems to exist in some state which is not commensurate with what it actually was in the first place. So like your Star Trek teleportation. If you want to see why it works, in the actual lecture notes, I do a kind of detailed and perhaps overly complicated calculation, but there's a simple way to see it. So this measurement onto in the psi j basis, if you get outcome j, it projects the quantum system onto the state psi j. And what is the state psi j? Well, it's sigma j acting on a maximally entangled state. And so here I've drawn the the quantum state in the other direction. So what I mean is actually the projection. With all of these circuits, we should instead of making them go from right to left to right, we should make them go from right to left, and then the Brockett notation would make more sense. But this object here is supposed to be denote projection onto the quantum state phi. The maximally entangled state has a property that you can just verify for yourself, which is that if you have some matrix and you act on one half of that maximally entangled state, it's the same as acting with the transpose on the other half. Okay, so you can just do that calculation. It's a simple thing, but we can use that identity to move the sigma j. Actually, I want a little bit more down below. One sec. We can move the sigma j from the S system to the A system at the cost of making it be transposed, right? So we can use our identity to put sigma j there instead. But then we have a maximally entangled state again. And so we can use our identity to shift sigma j transpose to this side. And of course, you know that the square of a Pauli operator is the identity. And so this whole situation amounts to doing nothing at all. And the quantum state phi comes out the end. And so that's quantum teleportation. So again, entanglement is enhancing communication in a very interesting, non-trivial way. In this case, turning a classical channel into a quantum channel. Are there questions about that?
I have a question.
Sure, yeah, go ahead.
So can I think of this as being like some way to encrypt a message?
Yes, you can. So the classical message that you're transmitting is completely independent of the quantum state in the S system. If it were not, then the measurement would actually cause a disturbance to the state. Like for this whole thing to work, it's crucial that when you perform the measurement statistics are independent to the state. So there are 4 possible values of J and they're equiprobable. And so, yeah, this is a method of actually securely sending. Not only do you transmit, but you transmit securely, provided that Alice and Bob have verified that they have this entanglement. So yeah. And I should mention again, just for context, that there was a very interesting paper a few years ago about extracting information from black holes in ADS-CFT by coupling the two sides of the two sides of a two-sided black hole. And the mechanism that is at work there is actually very similar to this mechanism of teleportation. And so you can look up the papers by Jafferis and then Douglas Stanford, who's teaching this course, and others. So another question?
The classical message sent from Alice to Bob is basically information about which Pauli matrix was used to measure to act on her own state.
Yeah, so it's a measurement. The measurement is defined by there being 4 orthonormal states, and this is a pair of qubits, so it's a 4-dimensional quantum system. So it's just it's just the simplest, most vanilla kind of measurement that you first learn about. It's a basis measurement, and you just send but the elements of the basis are in 1-to-1 correspondence with these Pauli operators. In fact, the elements of the basis are made by acting on a single state by the Pauli operators. Does that answer the question?
Yes, thanks.
Okay. So not the last, but one last interesting thing that I'll tell you about that you can do with entanglement is that it can help you win in certain kinds of games. And I'm going to introduce the concept of what we call in quantum information a non-local game. And the situation is that there's a referee, and there's an Alice and Bob, and Alice and Bob are separated from each other. So that's what the dotted lines depict. And the referee is going to give an input X to Alice and an input Y to Bob. And then Alice is supposed to do something depending on her input. And then she's supposed to provide an output A. And Bob is supposed to do something depending on his output Y, or input Y, and provide an output B. Now, this is called a non-local game. There are different ways of formulating this, but for the purposes of this class, we imagine that Alice and Bob are actually space-like separated for the entire exchange. So it's impossible for Alice and Bob to actually send a message to each other, without violating relativistic causality. And so instead of thinking of a single referee, you should probably think of like a guild of referees who decide ahead of time on what the questions are going to be. And one of them is close to Alice, one of them is close to Bob, and they hand them the questions at the appropriate time, and they collect the answers. And they now, for this to be interesting, we have to define what it means to win. And there's just going to be some function, and it maps the possible X's and Y's and A's and B's, the inputs and the outputs. Just for each collection or each setting of the inputs and outputs, the function just tells you whether Alice and Bob have won or lost. And so they're acting cooperatively here. They're not competing against each other, they're competing, if you will, against the referee, right? They're just trying to see if they can achieve A's and B's, or if they can output A's and B's that actually make them win. So an example would be somehow achieving superluminal communication, right? We've said that they're space-like separated, so there's no way for them to communicate, without violating relativity. But the superluminal communication game would be that they win if, let's see, I'll say if A equals Y and B equals X, right? So X is given to Alice, but somehow Bob manages to output X, and Y is given to Bob, but somehow Alice manages to output Y, like that. And so this would be the winning condition. And well, pretty clearly, the only way they're ever going to be able to win in this game is if if maybe physics is different than, radically different than we think it is, and there is some mechanism for them to be able to superluminally communicate. Okay. Now I'm going to define another game, which is going to look really weird. But there's a reason for it. And so they're going to win if a certain condition holds, which is that X times Y is equal to A plus B mod 2. And I should say X, Y, A, and B are all bits. So they just take the values 0 and 1. So this looks like a really strange condition. It might be a little bit more intuitive if I express it this way. So A should be equal to B unless X equals Y equals 1. Right? So for most settings of the inputs, Alice and Bob are just always supposed to produce the same output. But if they happen to be given the same inputs, then they're supposed to produce different outputs. Now, if you think about how Alice and Bob would play this game, let's just imagine that the inputs are randomly, uniformly distributed. So each possible pair of X and Y occurs with probability a quarter. Alice and Bob could just always output 0, say, right? And then 3/4 of the time, they're doing the right thing because their outputs are the same. Except that on occasion, Alice and Bob, a quarter of the time, are both given 1s as their input, and then they're wrong because they were supposed to produce different outputs. And pretty clearly, with a little bit of reasoning, a little bit of thinking, you see that the only way it seems for them to win at this game 100% of the time is again to have some kind of superluminal communication, right? Because on some occasion, Alice is going to have to do something depending on Bob's input if they're going to always win this game, right? Because they have to do something different in the situation where they both have the same value as their inputs. And so that they're only going to know if they both have the same value if there's some superluminal communication. On the other hand, so it seems like to win this game 100% of the time, you need superluminal communication. Being able to win it doesn't mean that the capability to play the game would be useful for superluminal communication. So you could imagine that someone had manufactured some mysterious black box that Alice would hold one, two black boxes. Alice would hold one side, Bob would hold the other side, and they'd put their inputs in and they get their outputs out, and they'd always win this game 100% of the time. And you might think that would give you a way to superluminally signal that they could somehow figure that out, but it doesn't. I'll just show you why. That if the A bit is always uniformly distributed, just probability a half 0, probability a half 1, the B bit could be A plus X times Y. And then they satisfy the winning condition, but Alice's bit is uniformly random, Bob's bit is uniformly random. And so they're never able to actually send messages from one to the other. They just have some, they're capable of, they have some interesting kind of correlation. So this is what we call the CHSH game. And those initials may be familiar to anybody. Anyone want to make a guess of what CHSH stands for? stands for Clauser, Horn, Shimoni, and Holt. And the reason is, they didn't define this game, they defined a Bell inequality. So this is another way of talking about Bell inequalities. So we can say the value of a game is the maximum winning probability. And we'll call it omega. We'll call it the value omega. So you optimize over all possible strategies for playing the game, and the maximum winning probability is going to be omega. And I'll put an omega C for classical. So for CHSH, we just more or less found that it's 3/4, right? That you can't do better than that. Now, or you can't do, you couldn't do better than that in a classical world, but the world is not classical, it's quantum mechanical. And we said that Alice and Bob are space-like separated, but that doesn't prevent them from potentially sharing entanglement ahead of time. And given the input X, Alice would perform some measurement on her half of the entanglement that depends on X, and then would get an outcome and will report the outcome labeled by A. And likewise for Bob with Y and B. And that defines the quantum value of a game. And I guess I just wrote this up above. So the classical value of CHSH is 3/4. But the quantum value is strictly larger if they're allowed this entanglement. It's about 0.85. And what this, the fact that there's this strict, this gap between the quantum value of the game, and the classical value of the game, this translates into the fact that what we call locally realistic theory can reproduce the predictions of quantum mechanics. What does locally realistic mean? Well, it means that the kind of reasoning that I gave here for why we couldn't win with probability more than 3/4 in the CHSH game actually applies to the underlying theory of physics. And so when people talk about local hidden variables, they're basically just saying that, they're saying that signals can't propagate, or influences can't propagate faster than the speed of light, and systems have well-defined states before you've measured them, which is the implicit assumption that went into deriving this 0.75. Quantum mechanics doesn't simultaneously satisfy both those properties, and so it turns out that you can have a quantum value which is strictly larger. Now, this is not super important, but just in the interest of putting you in touch with some recent developments, which were actually quite interesting and exciting, we could refine this story a little bit further. So instead of just the quantum value, I'll define something omega Q tensor product. So that is that's going to be the maximum winning probability if you assume that subsystems are modeled by tensor products in quantum mechanics. Okay, which is what we typically do if you take a course on quantum mechanics. Subsystems are modeled by tensor products. But if you take a quantum field theory course, it's more common to have subsystems being modeled by the commutativity of the operators on those different subsystems, right? And so subsystems are modeled by having commuting subalgebras. In the finite dimensional setting, these are the same thing. One implies the other, or one is equivalent to the other. But in infinite dimensions, they're not quite the same thing. And it was recently proved that there's a strict separation between these two values for a game. And so in particular, really, there exists some game, G, such that this commuting subsystems value is strictly larger than the tensor product value. And where does it come from? I'm not even going to bother getting into the details, but it comes from quantum complexity theory. So a recent, very impressive result in quantum complexity theory, which was basically showing that something called an entangled multi-prover interactive proof system could resolve the halting problem. So here's the oops, that's not what I wanted to do. So there's the reference if you want to look at it. So it turns out these statements are pretty much all equivalent. It also implies something, and the reason I wanted to share it with you is because there's a little bit of an irony here, that if you've ever met quantum information theorists, including me, they have this tendency to always work with matrices, right? And in finite dimensions. And that's partly historical, that when you're talking about building a quantum computer, you're only going to be, you can only stabilize the finite dimensional systems. And so there are reasons to restrict yourself to that case. But there is a sense that quantum information theorists are less comfortable with the continuum, say, than most other physicists. But there was this conjecture in operator algebras that had been around since the 1970s, widely believed, and it was a statement about von Neumann algebras, that were well behaved, so that had we don't need to worry about the definitions, but that had a normal, faithful, and tracial state, that they could have generating sets that were approximable by matrices. So this is the kind of statement that a quantum information theorist would like. It's the kind of thing that many physicists secretly kind of believe, that the world, can be well approximated by finite dimensional things, but it's convenient to use the continuum. But it turns out that some quantum information theorists, by virtue of proving this complexity theory result, disprove the Kahn embedding conjecture. So there are von Neumann algebras, that are well behaved in this sense, that cannot be approximated by matrices in any in any kind of useful sense. And so that had been open since the 1970s. It was one of the central open questions in operator algebras, and it was ultimately resolved last year using quantum complexity theory, in a result that basically can also be translated into a statement about how strong Bell inequalities can be. Are there questions about that? Again, I just wanted to give you some background, so I don't expect you to understand exactly what I was saying there.
Yeah, I have a question.
Yeah, go ahead.
Is that believed to be represented in the real world?
Probably not representative of quantum field theory, because I think that axiomatic quantum field theory often has something called the split axiom included. And I think that the split axiom, at least if you were talking about subsystems that were spatially separated and not touching, would actually exclude these counterexamples. But whether it might be true in string theory or in these other, I don't know. Yeah.
Okay.
Yeah.
Thanks.
Is it? Do you know that this does show up if you don't assume the split property? Because in a certain sense, I know that the axiomatic quantum field theory community sometimes assumes that axiom, but there are examples of things you might reasonably call quantum field theory that violate the split property.
So we don't know that it necessarily shows up, because right now there's just, they construct this very specific family of games. Or rather, they construct this proof, these proof systems that can be translated into games, and I think that the algebras associated with them are not like they're abstract mathematical objects right now, and so no one has made the effort or of thinking about really how you would translate it into a physically realizable situation. Like the number of this X and Y, the inputs are not bits in these examples. I forget, they're like billions or trillion, like they're huge input sets in order to get this to work. But it would be, it is at this point now a very relevant and interesting question to ask. Could you realize this in some in some plausible looking physical system?
Yeah, in particular, do you think this means we're supposed to change our intuition that continuum quantum systems are well modeled by limits of discrete quantum systems in general?
Well, I don't think we should necessarily change our intuition, because in many cases it's in many cases it's true, and you can actually do it. Like you can actually do lattice quantum field theory or things and get good results. And so all it should tell you is that whereas you or a mathematician might have believed this would always work in situations of interest, you should now be, you should have an asterisk on that belief, and future work will determine how large and worrisome that asterisk should be. Yeah.
Sure. Thanks.
Okay. All right. So now I'd like to move on to error correction. There's a lot more to say about entanglement. And if there's time, in particular, I haven't spoken about mixed state entanglement, multipartite entanglement, but I think it's more important right now to move on to error correction. And if there's time, there won't be, but at the end of tomorrow's lecture, we can talk more about mixed state entanglement, or you can ask me questions and I'm happy to answer. So again, the real motivation for thinking about quantum error correction, or there are different motivations, but it's really played a very useful role, or an important role in understanding holography. And the reason it's played an important role is one, understanding how to map bulk observables to boundary observables. This ends up being a question of error correction. Understanding how locality arises in the bulk. This is also related to error correction. Understanding why entropy can be related to area. Why entropy, which is not an observable, can seem to be well approximated by something that is an observable area. All of these questions in holography were ultimately understood properly by thinking of quantum error correction. So this is a tool that you want to have in your tool belt. Today's discussion of error correction is just going to be basically trying to understand why error correction is possible. And we'll develop more formalism next day. So what is error correction? How is it even possible? And then next day, we're going to be talking about things called stabilizer codes, which give us lots of nice examples. Something called the toric code, the GKP oscillator code. And we're going to talk about why quantum error correction appears naturally in many cases in many body physics. Okay, so the warm-up. Let's just think about classical error correction. So suppose that I had a situation where I was going to send a message, but there was a possibility that a single bit was going to get flipped. So can anyone give a suggestion for how my message is going to be a single bit, and maybe I'm allowed to transmit many times? What could I do to be robust against a single bit flip?
Well, you can add one bit with like the sum of them.
You're ahead of me, but yes. So you could do that. Yeah, so you could do a parity. I want to be more simple-minded for the moment, but your suggestion is actually the better one than mine. You could just repeat, right? So if I wanted to send 0, I could send 0, 0, 0. If I wanted to send 1, I could send 1, 1, 1, right? And of course, then you decode by majority vote. But the suggestion was a great one, and it's going to play a major role later. And just to introduce notation, I'm going to call 0, 0, 0 my logical 0, and I'll call 1, 1, 1 my logical 1. Right? So it's just the encoded 0 or the encoded 1. And so the fact that you can do error correction classically is no mystery at all, right? Like you can, like I asked you the question, how would you do it? And you immediately gave me an answer which was better than my suggestion. But just repeating the messages, it gives you some robustness classically. Does anyone see an obstacle to using the same strategy quantum mechanically?
No cloning theorem?
Yeah, exactly. So the no cloning theorem tells you that you can't copy quantum mechanically. So the same thing, it can't work in the same obvious way. Another obstacle is that the errors are not discrete, right? There's an infinite, there's a continuum of things that can go wrong with your quantum system. It could be rotated by 1/1,000,000th of a degree. It could be erased, whatever. It could be rotated, the angle at which it's rotated. It could be coupled to some environmental system. So the errors, and the state for that matter, are continuous. Anyone else see any obstacles in quantum mechanics potentially to getting error correction to work? Again, I mean, at the outset, something that you might worry about. Oh, sorry, was someone saying something?
making a measurement destroys information about the prior state.
Yeah, exactly. So measurement causes disturbance. Right? You couldn't do a majority vote because that would require that you actually learn what the state is. And so on the face of it, quantum mechanics and error correction don't really seem to be well matched to each other because these three basic properties of quantum systems seem to be working against you when it comes to making error correcting codes. Now, this section of the course is all about quantum error correction, so you shouldn't worry. There are ways around all of these obstacles. And we'll get to that in a little bit. But before we get to it, I want to let you work on a worksheet. And the worksheet is actually just about classical error correction in one of the simplest channels, so the classical erasure channel. And I just want you to get a feel for how it works. So I minimized the interest in quantum error correction. At the beginning, I said, yeah, or classical error correction, like, yeah, you can do it, big deal. But even classical error correction is pretty interesting. And so this is worksheet 3. You can download it from the wiki, and I'll send you out, but if anyone wants to ask a question, you can stay behind while others start on the worksheet. So I'll assign automatically. Let's see. Okay. And I'll try to circulate a little bit, and I'll give you 15 minutes to work on that, and then we'll come back.
This is going great, by the way.
Hello.
Hey,
Sorry, my laptop's battery died. Could you please put me back in breakout room 8?
sure.
Thank you.
7 to 8. Okay, there you should be there.
Thank you.
And you, Sergio, did you want to go to anyone? You'll stay here with us.
I decided to stay here this time.
Sounds good.
Oh, thanks. Okay, so everybody's back. So this is a situation, one of the simplest models of noise you could encounter is just this eraser channel. The bit gets erased with probability P, and when it's erased, you know that it's been erased. And you think of using this in a situation where you can access this channel as many times as you like. Every time you access it, the erasure happens independently of the other times. And imagine trying to use it with a repetition code, meaning you just you have a message you want to send and you repeat that message L times, and then you move on to the you repeat the first bit L times, then the second bit L times, and the third bit L times until you've used up n uses of the channel. And the first question is show that the error probability does not vanish in this model if L is fixed. And it doesn't, the erasure probability, even for the first message bit, doesn't vanish, right? Because with an erasure, with these repetition codes, the recipient will be able to decode the answer, provided not all of the bits have been erased, right? That if you repeat the bit 25 times, if it's erased 24 times and you get the 25th one, then you can still decode. So the probability of not being able to successfully decode the first message bit is just going to be the probability that the transmission was erased all L times, which is P to the L. That could be a small number, but it's a number which is independent of the total number of channel uses, which was this fixed number n. And so the error probability does not vanish in the limit of large n. And so the repetition code was easy to write down, but it's certainly not the end of the story in classical error correction, because it's not optimal, and it doesn't even, if you're thinking about the capacity, the optimal rate of data transmission in the under the constraint that in the limit of large messages, the probability of error has to go to 0, the probability of error does not go to 0. So
is that is there maybe a typo in the problem statement, because it asks to say that show the probability is that it's sent without error doesn't vanish? Should that say with error doesn't vanish?
No, the probability. Oh yeah, so no, there is a typo, and I apologize for that. It's not this. It's probably I should just have removed x1 through xn. So the fixed message that you're trying to transmit and that you encoded into the repetition code, the probability that is sent, does not go to 1. I apologize. I put this together late last night, that it is sent, that it does not go to 1. So I hope that didn't disorient people too much. So the probability, I should just say that the probability is sent, the probability of error does not vanish. Okay, so now I say if you have n uses of the channel, what is the expected number of unerased bits, right? So, well, the probability of erasing a bit is P in a single use. The expected number of erased bits is n times P. The expected number of unerased bits is n times 1 minus P. Okay. And then the question is, if the sender somehow knew in advance which bits would be erased, what rate of transmission could she achieve? Well, she would just not use the slots where she knew that the transmission was going to be erased, and she'd have roughly n times 1 minus P slots left where the transmission was not going to be damaged, and she just send in those slots, and the receiver would just ignore the slots where he saw an erasure, and the receiver would receive the message. And so the number of transmitted bits would be about n times 1 minus P. The rate would be 1 minus P. Right? Now, of course, that's not what really happens, right? Like the sender doesn't know in advance where the erasures are going to occur. But the famous theorem of information theory by Claude Shannon, he showed that the capacity, the optimal rate under the constraint of vanishing error for large messages, is bounded below by the mutual information between the input X and the output Y for any distribution on X, right? So if you fix a distribution on X, then you get a joint distribution on inputs X and Y by just using the transition probabilities for the channel. And the mutual information is just that, it's a special case of quantum mutual information. If you have a random variable X, then its entropy is just minus the sum of P of X times log P of X. And we'll evaluate the log space too, because we're interested in measuring information in bits. And so the question is just to show, to ask if the input is uniformly distributed, what is this mutual information? And it's a calculation, which I don't know if it's really worth going through. You just substitute things in, and you get these three entropies. And the mutual information, remember, is the first entropy of X plus entropy of Y minus entropy of XY. So you look at that, and what comes out? Well, the entropy of X is 1. And these pieces and the entropy of Y and entropy of XY cancel. And so what you're left with is minus P log P plus P log P over 2, right? And because the logarithm has taken base 2, this is 1 minus P. And so this is actually, this point is often not driven home when people take information theory. Shannon's result is amazing, right? What Shannon's result tells you is that there are codes out there that are as good as knowing in advance which bits are going to be erased, right? So you don't need to know in advance which bits are going to be erased. You're going to be, if you use the right kinds of codes, you're going to be able to transmit as if you knew in advance. And they involve parity checks of the type that somebody proposed. And so error correction, and I just wanted to give you, I just wanted to get you excited about it, right? That there's it's more powerful than you might have thought it is. Okay. As always, I go more slowly than I intended. But let's just start on the simplest simplest little quantum error correcting code. And it's not going to achieve a lot. It's just going to be a quantum version of that repetition code. And what we're going to do is, if it's going to be a code on a qubit, and if the input was 0, we're going to map that to 3 zeros. And if the input was a 1, we'll map it to 3 ones. This does not violate the no cloning theorem, because I've just told you what an orthonormal basis goes to. And then linear superpositions will map to superpositions. So I'll call that my logical 0 and my logical 1. And if my input was alpha 0 plus beta 1, then my code is going to be, or my code state is going to be alpha 0, 0, 0. I'll drop the extra kets plus beta 1, 1, 1, like that, right? So this is not violating the no cloning theorem. This is a linear transformation that preserves the inner product. So that's perfectly allowed. And what we'll think of as the code is going to be a subspace of the whole Hilbert space. So it's just going to be, as I wrote, alpha logical 0 plus beta logical 1. And it's a subspace, a 2-dimensional subspace of the 8-dimensional Hilbert space. Okay. So that's going to be what we call the bit flip code. And just introducing some notation here, I'll write x sub 1 for the Pauli x operator acting on the first qubit, x sub 2 for the Pauli x acting on the second qubit, and so on. And so then, for example, x3 acting on, and I'll call this the logical quantum phi up above. So phi3 acting on phi logical will be what happens if I flip the third bit, 0, 0, 1 plus beta 1, 1, 0. Right, so this is a kind of error that could occur in this code. And now let's just restrict ourselves. We're not going to be ambitious yet. We're going to have to wait until tomorrow to be more ambitious. So let's just suppose that one of x1, x2, or x3 acts on a logical qubit. And the question is just, is that correctable? And we've already, we've just seen here that the no cloning theorem is not necessarily an obstacle, as long as we, because we can copy in a fixed basis. So now we're going to ask, is the fact that the quantum state is not discrete, right? That it's actually any number of an infinite number of, or it's an entire subspace of states. Is that a problem? So let's just ask, can we correct these bit flips? And well, we're going to have to measure something to figure out whether, how to correct. And if I look at the state which was caused, or rather the state which resulted from this, this error operator x3, this bit flip operator, it's an interesting state. It's in a, it's in a subspace which is the span of 0, 0, 1 and 1, 1, 0, right? And the original code was the span of 0, 0, 0 and 1, 1, 1. And so I can start writing down some projectors. Oops. So I'll call the first one pi 0, 0, 0. And this is just the projection onto the code subspace. And when we perform our measurement, we see that means that none of the bits were flipped. And so we should do nothing. On the other hand, if say I define pi 1, 0, 0 as the projector onto the subspace corresponding to flipping the first bit, what action should I take if I get that outcome? I'll just ask you. If I was in this subspace where the state was a linear combination of 1, 0, 0 and 0, 1, 1, which meant the first bit was flipped, how could I fix that error?
By x1.
Yeah, I'd flip it back like that. And so likewise, I'll have two other projectors. If the second bit is flipped, I correct by applying x2. If the third bit is flipped, I correct by applying x3. And so, yeah, these errors are correctable. And it wasn't a problem that the quantum state is continuous, because what I did is I measured the error. I didn't measure the state. And so because I measured the error, and I learned only about the error, I didn't learn anything about alpha and beta, I didn't disturb the state. Now, this is kind of a cumbersome way of talking about the measurement. So a nice way to talk about this is to identify where the bit flip happened by measuring parities, right? So I can measure the parity of bits 1 and 2, right? Whether they're the same or different. And I can measure the parity of bits 2 and 3. And as observables—
Just a question.
Sure, go ahead.
This may be very naive and I may be being silly, but in order to know what to apply, don't we need to disturb the state by applying one of these projectors?
You might disturb the state. Like it might have been a superposition of multiple single qubit errors. But I'm saying it at the moment to start. Let's just hypothesize that what happened was one of these three things. And that means that I'm always in one of these 4 subspaces. Either nothing happened or so I'm later tomorrow we'll think about the more general case of arbitrary errors. But right now I'm just being very unambitious, and I'm only trying to correct against a single bit flip. And it's isolated in a single position. So the way that I measure the parity of bits 1 and 2 in this 0, 1 basis.
Patrick, can I just let you know? Sorry, we didn't give you a warning, but it is 3:15. So
yeah, I'm just going to finish this page and then I'm done. Okay, so the parity of the first 2 bits is the observable Z1 times Z2, right? Z1 is eigenvalues +1 and -1. +1 corresponding to 0, -1 corresponding to 1. So this will be -1 if the parity is odd, and +1 if the parity is even, and likewise Z2, Z3. And so when the bits 1 and 2 are the same, when I measure Z1, Z2, I'm going to get a 1. When the first two bits are different from each other, when I measure Z1, Z2, I'll get a -1. So I'll get a -1 here, and I'll get a +1 here. And likewise for Z2, Z3, +1. Now the second two bits are the same, so I still get +1. And now the second two bits are different, so I get -1 and -1. And so those 4 projectors correspond to the 4 different pairs of things that can happen here. And since these are commuting observables, measuring these 2 observables, they're compatible, and measuring them is equivalent to performing the other measurement. And so that's the story of what I'll call the bit flip code. We can correct for all of the states in this subspace, provided we have this very limited error model. And next day, we'll see how we can bootstrap from this very simple error correcting code into correcting arbitrary errors on a single qubit where anything could happen. And I should stop there. And so I'll open the floor to questions now.
Thank you. So questions?
I should admit that this is probably not that impressive. Right, this is just the translation of the repetition code into compatible quantum language. But it turns out that it's not that far from this observation to something much more interesting.
Okay.
And you can ask about anything from today's lecture, of course, or anything at all about quantum information. Go ahead, Marcos.
Okay, it's the question about, I don't know if Marcos doesn't have a.
Oh, what was the definition of n in the exercise after? So the definition of n was just the number of times the channel was used. Yeah.
Any other questions?
Can I ask a question?
Yeah, go ahead.
Could you explain one more time why what you've written underneath the bit flip code isn't violating this no clone theorem?
Oh, sure. Yeah. So how do you define a unitary transfer? Well, this is not actually a unitary transformation. This is going to be an yeah, so actually it's worth spending a little bit of time on this, right? So when we spoke about quantum channels are the things that you're allowed to do, as we saw earlier. And what is the condition in a quantum channel? N of rho has to be sum over nj, or sum over j nj acting on rho by conjugation, right? And we also had the condition that sum over j, nj dagger, nj was the identity. So the special case of this, in which there's no, there's a special case where there's no sum over j.
Okay.
Right?
Yeah. Yep.
So I'll just eliminate the j's.
And n is just a unitary.
My pen is not very precise there. Okay, I'll fix that. So it's n acting on rho by conjugation. And n dagger n is the identity. So this looks like the condition of unitarity, right? But remember that n doesn't have to be a square matrix, right? And so as long as what this is saying is just you have to preserve the inner product.
Okay.
And so what I have here is a transformation that actually expands, it goes from a 2-dimensional Hilbert space to a 3-dimensional Hilbert space.
Okay, so you're
but it preserves the inner product.
Okay, so
right? Because I just take
it.
Like I define how it acts on a basis, and then that, and then I extend by linearity to all other vectors.
Okay.
So this line here is just saying I extend by linearity, because I just and so if I have a transformation and it preserves the inner product on the basis vectors, then it preserves the inner product on all vectors.
Right. Right.
If it takes orthonormal to orthonormal, then I'm done. And so this is perfectly fine, perfectly allowable. And I could even explicitly write down the matrices for you without, or well, I sort of did, but I could even write it as a unitary transformation with, another way of thinking about it is that I start off with 3 qubits, and 2 of them are in some fixed state. So like the first one is my input qubit, and then the other 2 are just say in the 0 state. And then I could write down a unitary transformation, which implements what I want to.
That's what I was going to ask, is if you could just think of it immediately as having 3 qubits, and you just put your state as the first qubit, and then you prepare this transformation that's going to kind of duplicate.
Yeah. So let me do that.
Yeah.
So if I want to have this transformation here, 0 goes to 0, 0, 0, 1 goes to 1, 1, 1, right? And I'll have 3 qubits, and I'll start these ones out in the 0 state. And then this one is going to be some alpha 0 plus beta 1. So that's the one that I'm interested in.
Okay.
So I'll just define a symbol here. We call this the controlled NOT gate. And what this does is if there's X and Y, as your inputs, then you get Y plus X, not 2. Right, so you, so what this amounts to is if the first qubit is in the 0 state, you do nothing. And if the first qubit is in the 1 state, then you flip the other qubit.
Okay,
right?
yeah.
And this is unitary. You can just double check. And so here's what you would do. And it's pretty clear that this will do the job, because if the first qubit was in the 0 state, nothing happens ever. And you started off in 0 and you get 0, 0, 0 as your output. If the first qubit was in the 1 state, then you first flip the second qubit and then you flip the third qubit. So you end up with 1, 1, 1.
Okay.
And so, yeah, that if you wanted to implement it, using these 2 qubit gates, like on a quantum computer type situation, this is what you do.
This is great. Thank you. Yeah, that helped a lot.
Okay. Yeah, no problem.
Can I ask another question? Probably.
Sure.
Sorry.
Probably I missed probably I missed something simple, which is why, when you measure Z1, Z2, or Z2, Z3, as you did at the end, you cannot perturb the state. Isn't it true that you're gonna collapse the state either on the 001 or 110, say, in the example you used?
Okay, yeah, good question. So when I say measure Z1, Z2, I don't mean measure Z1 and then measure Z2. I mean measure the observable Z1, Z2. And so the eigenvalues of Z1, Z2 are +1 and -1, and each one of those is 4-fold degenerate. Right? And so when I measure Z1, Z2, I split the Hilbert space in half. It was 8-dimensional, but I split it into a 4-dimensional subspace. And likewise for Z2, Z3. So if I first measure Z1, Z2, and then I measure Z2, Z3, the measurement of Z1, Z2 projected me down to a 4-dimensional subspace. The measurement of Z2, Z3 is going to split that 4-dimensional subspace in half, right? But I'll still be 2-fold degenerate. And that degeneracy is why I don't damage the superposition. Yeah.
That's clear. Thank you.
Hi. One question regarding the CHSH game.
Sure.
you said that you can win 100% of the time without having useful superluminality by making B a function of A, but A a random variable.
Yeah.
Wouldn't that still require like superluminality that breaks
Yeah. Well, yeah. So that
the variance because B is still a function of A.
Would it have to break Lorentz invariance? I'd have to think about that.
Or like break causality. That's what I mean. Like,
so yeah.
Isn't this useful superluminality if B is a function?
No. So the point is, imagine that Alice wanted to send a message to Bob, right?
Mm-hmm.
Or imagine that, so let's see, B is equal, yeah, so let's ask the question, does Bob receive any information about X, in his laboratory, right? And you could ask, for example, the random variable, the joint random variable, XB, right? What is its distribution? It's uniform on all four possibilities. Because you have to, when you average over A, which is unknown, you just end up with a uniform distribution for B.
But
and so
still
in
you
Bob's
can't-
lab, as far as he's concerned, he just has a uniform distribution, and he can't learn anything about X using anything that he has in his laboratory.
But also, but the main state, at least how I understand the problem with superluminality, is because you can't order the events. So you don't know which one happened first.
Okay.
That's the problem when events are space-like.
Yeah.
So how can I have B that's a function of A? So you can't do B until A happened. If A happened.
Yeah.
after.
So no. So I'm not proposing a physical theory where this would happen. I have no idea. Like, I don't think it's possible. I agree. But what I mean, and the language is a little bit slippery. Like, imagine some supernatural being, just supplied Alice and Bob with these devices that outputted A and B that were distributed as I proposed. My claim is that would not be useful for that would not give them the ability to communicate superluminally.
Okay, so it's more of a statement that the fact that they can win doesn't automatically mean that there is superluminality.
Correct. Yeah.
Or would you agree?
Not that this example works well. Okay.
Yeah.
I mean, would another way to phrase it be, if the A and B are determined superluminally according to the specification of the game, you still couldn't make any use of it?
Yeah, maybe that's actually better, Veronica. Yeah, because then you don't have to play this counterfactual. It's less confusing. Yeah. So if you had some theory in which there was, there were superluminal influences, but what you achieved was just what I wrote down here, that would still not allow you to send superluminal messages from Alice to Bob. They would just be able to establish some interesting correlations. Yeah.
But wouldn't that still break causality?
Well, quantum mechanics is a little bit of this character, right? That what you achieve in quantum mechanics looks a lot like this distribution, except that it's this with some probability, and then you have to mix in also some.
Well, no, okay. I guess
some uniform. You have to mix in some additional noise into this distribution.
So I guess that B is a function of A, but this is all semi-invertible. So if you
yeah, A is also a
switch
function
the
of B.
order,
Yeah.
yeah. So A is also a function of B. So if you invert the order of the events, you can consider A to be a function of B.
Yeah.
And because you didn't have interesting superluminal communication, that's all fine. Okay.
Yeah, I'm yeah. This is just defining a distribution, but yeah, that's right.
Yeah.
Yeah.
Thank you. That helps.
Oh, I see. Okay, now I see the nature of the equation. Yeah, so this looks like there's a preferred order here, but there's not.
Yeah.
Mhm.
Okay, and then there was a question in the chat, which you sort of already answered.
Okay, I'll read it here. So I believe it's, there's a question. Oh, can you explain again why the measurement of observables does not disturb the state we want to correct? Okay, so that question was actually asked in terms, and I answered in terms of degeneracy. But the intuition, that's kind of a mathematical answer. But the intuition is that in quantum mechanics, when you perform a measurement and you extract some information, you will damage, there will be an effect. There'll be back action on the quantum system, but there'll be back action in terms of whatever you learned, right? And so there will be some collapse of the state into the different possibility, into branches of the wave function that are consistent with what you learned. And in this example, what we learned was just which bit flip operator acted. Nothing x1, x2, or x3. And so that is information about the operator that acted. And if there had been a superposition of operators, and we'll discuss this next day, then we would have collapsed that superposition of bit flip operators into a single bit flip operator. But we didn't learn anything about whether the superposition was in the 000 branch or the 111 branch of the code, right? And because we didn't learn anything about which branch of the superposition in the code subspace we were in, the measurement is not required to collapse that superposition, right? That what quantum mechanics does, the way that collapse works is that you collapse the wave function into branches that are consistent with what you learned. And the 000 branch is consistent with what we learned, and the 111 branch is consistent with what we learned. So we don't collapse that superposition. Does that answer the question?
Actually, let me follow up quickly on if operationally you tried doing this, would you worry that there's some pollution?
Oh yeah, there's a whole story to tell here. We're not going to have time to get into it, but when you do quantum error correction, when you analyze it for real, right, you assume that everything you do is faulty, right? So your measurements are faulty, your state preparations are faulty, your coupling to the environment, like when people try to model this, they really are as pessimistic, they try to be as pessimistic as possible. And so then it's not enough to just say we measure the observable Z1, Z2. I'd have to say, how do you measure it? And when you measure it, how are those degrees of freedom coupling potentially to it? And so all of this has been analyzed, and and so here I'm talking about an idealized measurement. But there are good ways to measure and there are bad ways to measure, right? Like I just said, like a really bad way to measure would be to measure Z1 and then measure Z2, right? Because then that just fails. But even the story is much more subtle than that. Like you have to, you have to think about the sequence of couplings that would be required to perform to perform this measurement, and whether that itself could introduce some problems into the code. And yeah, so like there's a whole story of fault tolerance, which we won't talk about because it doesn't play any significant role at this point in quantum information, quantum gravity. But people do worry about these things and have thought them through very carefully. And it's an ongoing. It's interesting, actually, very interesting, in that if you were in the game of trying to help build a quantum computer, right? you can either be the person, among the people who try to improve the hardware, or the people who try to improve the software. And the software is, all of this fault tolerance stuff, which is going to have to run on top of these devices. And there's significant room to improve the fault tolerance constructions in such a way that the goalposts for the experimentalists move closer and closer to what they can actually do. And the best, some of the best procedures that people have come up with, they've come up with relatively recently, right? Like it's not like this was all invented in 1999 and they're just trying to aim for it. Like people have new ideas.
Great, thank you. Okay, we're running out of time. I suggest that we end the official recorded part and